I was going to say good morning, lads and ladies, but it looks like so far it's just you, Thomas. So good morning. I guess I'll wait a few moments for others to trickle in before getting started here. Hopefully they do that. It would be a shame if they did not. All right, here we go. Folks are arriving now. So we're going to get started in just a few minutes. Now, today was supposed to be Jacob's student teaching day. And unfortunately, he has kind of disappeared from the class. I tried to reach out, but I haven't heard anything yet. And I have not been given any materials, any sort of prep or rehearsals. So unfortunately, it looks like our final student teaching day is actually going to not be a student teaching day. I'm going to hold off on getting started because today is a relatively short lecture, and in the event that Jacob does show up and wants to lead the class, I want to give him that opportunity. So you guys can take a second, grab some coffee, do whatever you want to do. I will give Jacob until 11:05 to show up. These things do happen from time to time, although not usually in an honors class. I think Jacob may be having a difficult time with some stuff. Not that it's all. All right, so for those who are just arriving here, today was supposed to be our final student teaching day, but I haven't had any contact from the student who's supposed to be leading class. So we're just waiting a few minutes to see if he makes it. If not, I'll go ahead and lead the lecture for today. We're going to wait until 11:05. While we're hanging out, is there anything you guys would like to discuss? Any questions or concerns? Okay, Katie, yeah, fire away. Cengage has kicked me out, as is tradition, so I'll go ahead and get logged back in. Okay, let me turn on my screen share. I've got the homework put up here. So homework 16. Yeah. Anybody take a stab at number 16 yet? This U sub problem from last week? Version of it I see there is. So let me go ahead before you play. This is, of course, MAC2311 section OH1. That is a lecture. And today is the 12th of April 2021. Today, we'll talk about areas between curves, which we introduced last week, but we haven't seen a formal treatment of. That's section 6.1. Before I dig deeper, announcement. We also said this last week, but exam 3 will be next Monday, a week from today, which is the 19th in class. So if you guys took a look at the video posted last week, that does have all the good stuff in there, including the intro to 6.1, a little discussion of exam 3. There's something else I want to say. Oh yeah, jury duty, right? So I'm doing this jury duty shit. It's going to be a bit of a mess. I'm hoping and praying that it is over tomorrow, but I don't know for sure. It could go on for weeks. It could be a one-day thing. So I will keep you guys updated as this goes. Hopefully it does not disrupt things any more than it has to. But what I'm planning to do is if it does continue on, I will pre-record lecture videos. We don't actually have any more material after today. Everything after today is going to be like little odds and ends. There's like the mean value theorem for integrals and a few cool things that I want to share with you guys, then review for the final. But I'll pre-record things if need be, and then I'll move my office hours into the evening again if need be, because I know you guys need office hours coming up to this test. So I don't want to shortchange you there. So that's it. That's as far as announcements are concerned, right? Exam 3 is next Monday. I got someone for jury duty. Sucks. But we'll get through it. If you need help with anything, if you're feeling stuck, if you're unable to come to the new different office hours, just send me a message on Canvas and I'll work with you. We'll find something. So this homework problem, Katie wanted to look at number 16 from the homework, which as I'm seeing it here, we have x to the 9 over 1 plus x to the 20. So first, homework problem. Evaluate the integral of x to the 9 over 1 plus x to the 20 dx. Do you guys remember the e to the x over 1 plus e to the 2x integral we did on our first day of U sub exactly 1 week ago? Sorry. This should ring that same bell. It's like some shit over 1 plus some shit. And the shit down here is kind of like an even thing, an even power. It was e to the x over 1 plus e to the 2x before. Now we have a very similarly shaped integrand. Remember, that's the name for the thing inside the integral, the integrand, and that it's a thing over 1 plus a thing. The trick before was to recognize that e to the 2x is e to the x all squared. The trick here is going to be quite similar. And I did see a recommendation in chat. One of the suggestions was that we try to sub x to the 20 for u. If I did that, then du would be 20 times x to the 19. And that would work great if this was a 19, but it's not, it's a 9. So unfortunately, the sub for x to the 20 isn't going to be quite as nice as a slightly different sub. Yeah, exactly, right? So this should kind of remind you of arctangent, something over 1 plus something squared. So here's what I would do first. My brain, when I see anything of this sort of shape, starts to think of arctangent. So I want to write this as like 1 plus something squared downstairs. And conveniently, the power down there is even. So I can write this as 1 plus x to the 10 squared in my denominator like that. Is everybody comfy with the algebra step there? Remember the rule is that x to the a times b is the same as x to the a all to the b. Oop, off to the side there we go. So that's the algebra rule that allows us to rewrite the bottom in the way we did. And looking at it like this, now I do see kind of an inner and an outer, right? My inner is x to the 10, and we know x to the 9 is proportional to the derivative of x to the 10. So if I sub u equals x to the 10, du is going to soak up this x to the 9. So we're going to substitute u equals x to the 10th power. Let's zoom out just a little bit. That way, du will be 10x to the 9 dx. So here's my little substitution box. We can solve this piece here for dx. We'll get 1/10, 1 over, I'll write it like this, 1 over 10x to the 9 du is equal to dx, and then I can plug that in here. So we'll plug in the obvious stuff like x to the 10, that's u. I'll leave everything else in this step, including the dx. Once you've plugged in the piece that you've chosen for your substitution, you should look at everything that's left over and then plug in for dx. I've solved my differential here for dx. So this will be integral x to the 9 over 1 plus u squared times 1 over 10x to the 9 du. And then lucky us, the x to the 9s cancel. All of our x's go away when we plug in for the differential, so we don't have to do anything wonky. Remember those more challenging problems where you got to go back here and solve this for x or something? None of that. Everything goes through nice and smooth. I can pop out the 1/10. And what's left is 1 over 1 plus u squared du. So remember I said when I see an integrand of this shape, my brain immediately goes to arctangent. This is actually the derivative of the inverse tangent or arctangent of u. So the indefinite integral of 1 over 1 plus u squared du is 1/10 times the inverse tangent, or you can write it as arctan if you prefer that notation, of u. And at this stage, we need to write our plus c. Am I done? Am I done, or is there more I need to do here to solve this problem? Or should I ask other questions up to here? So from the silence I infer there are no questions. Yeah, and that's kind of what I'm asking, Thomas. So is there anything else I have to do here? Yes, there is. We're not done. Because this is an indefinite integral, we do need to plug u back in. So this would be 1/10 the inverse tangent of x to the 10 plus c. And the answer to Thomas's question in chat, do we have on a test, do we have to plug u back in? For a definite integral, an integral with bounds, no. With a definite integral, we change our bounds when we make the substitution, and then we would evaluate this expression between those bounds. But with an indefinite integral, the kinds where you write plus c, the kinds with no bounds, when you make a u sub in those, at the end, you do have to plug back in. So there's a difference between indefinite integrals and definite integrals when it comes to substitution. All right. I do think we're past 11:05 now, and I still don't see Mr. Law. So it does appear to be the case that I will be lecturing today instead of Jacob. That's fine. So let's go ahead and get to it. First, are there any questions on this example that we started with here, this problem from last week's homework? So areas between curves. We talked about this a little bit last week in the not so live lecture, but I want to go through and give a formal treatment and solve some examples today because things can be a little bit more complicated than they appear at first. If we want to find the area between two curves, each given as a function of x, so like y equals f of x and y equals g of x, from x equals a to x equals b. This is not too bad. Formally, we calculate the integral from a to b, absolute value of f of x minus g of x dx. That's it. That will be your area. However, the absolute value of f minus g is a slightly weird animal, where absolute value of f of x minus g of x is equal to f of x minus g of x if f of x is greater than or equal to g of x, and it's equal to the negative of that, which is g of x minus f of x if f is less than g. This is really just the definition of absolute value. The absolute value of some shit is that shit, if that shit is positive, and it's the negative of that shit if that shit is negative. And these are just different ways of saying that f minus g is positive and f minus g is negative. But in practice, this isn't so much how we do it, because writing this step down is not super helpful. It doesn't really do anything. So what we saw was that in practice, and I'll do this in some color, we need to determine which function is on top of the other. So in blue here, I'll call this f of x. This, of course, is the x-axis. And then in orange here, because it's Gainesville, I'll call this g of x. Maybe A is over here. Maybe B is over here. So the area that I'm after is all of the area between these guys. Which is all of this stuff together with all of this stuff. So the way that people remember how to do this isn't by thinking of it as the absolute value of f minus g. You think of it as the upper function minus the lower function. That's really what this is saying. The thing you're integrating here, absolute value of f minus g, is equal to f minus g if f is bigger than g, meaning if f is the upper and g is the lower, you integrate f minus g. And it's equal to g minus f if f is smaller than g, meaning g is the upper function. So it depends on who is the upper and who is the lower, or better, which function is outputting the larger values. So one of the important steps in many of these problems is finding any intersection points. In practice, the way I would compute this area is as the sum of these two areas. I call this first guy A1, and I call this second guy A2, then A1 would be the integral from little a to little c of the upper function minus the lower function. And from a to c, f is the upper and g is the lower. So this would be integral f of x minus g of x dx. And a2 would be the integral from c to b of the upper minus the lower. So here g is the upper and f is the lower. So this would be the integral from c to b of g of x minus f of x dx. The only utility of this expression is that it kind of encapsulates all of this. It is maximally general, but it's not maximally useful. Because the only way to integrate absolute values like that is to think about which one is larger and then split it up. So this is usually how people think of it. If one function is always bigger than the other, then you just integrate the upper minus the lower. And if they do ever trade places, then you need to split up the integral and handle each one separately. And there's an example like this in the video from last Friday, where sine and cosine are used from 0 to pi. And if you haven't seen that, please do go look at that immediately after class today. But today my goal is to extend a little bit further from where we went in last Friday's class. So that is what we're going to do. Two big goals today. First, solve some kind of challenging problems of this nature. And then second is to see what happens when we're not in this scenario. So here we were said if we want to find the area between two curves, each one given as a function of x, right? Y equals some function of x, then we can do it like this. But what if I kick out this statement? What if I don't assume that these are both functions of x? What can I do then? So we'll look at that as well. But first, some problems of this nature that are at least somewhat challenging. The problems like this that I most like are the ones where they just say, find the area of the region enclosed by these curves, because they're asking you to sketch and figure a bunch of shit out for yourself. So we're going to come back to some of the example problems here, but only after looking at some of these. All right. I think a good problem to begin with would be number 9. So they say, sketch the region enclosed by the given curves, decide whether to integrate with respect to x or with respect to y, draw a typical approximating rectangle, label its height and width, then find the area of the region. So the curves here are 1 over x, 1 over x squared, and x equals 2. So here's how I would say this. Find the area of the region bounded by the curves y equals 1 over x, y equals 1 over x squared, and x equals 2. So there's some graphing involved, right? We need to sketch the graph to even have a clue what we're doing. There's some geometry involved. We need to figure out whether we're going to, how we're going to think of that region. Is it an upper minus a lower? Do they trade places? That sort of thing. And then, of course, there's the calculus step where we do the integral. First, the graphing. Here's 1 over x. This is a graph you should know. This is something I make my college algebra students learn. Of course, there's another piece kind of over here, right? It's a rational function. The denominator is 0 when x is 0. It has horizontal asymptote y equals 0. This is 1 over x. 1 over x squared looks very similar. In order to tell them apart, mark this as 2. 1 over 2 squared is 1/2. So this guy right here is 1/2. 1 over 2 is 1/2. So yeah, this is the point 2 comma 1/2 along the graph y equals 1 over x. 1 over 2 squared is 1/4. Should be half as small as that. But 1 over 1 squared is still 1. So 1 over x squared is like steeper in here. And then it sits down a little bit harder on the x-axis than regular old 1 over x does. So this is 1 over x squared, and this is 1 over x. X equals 2 is a vertical line going through the point 2 comma 0. So here is x equals 2. Which means that my region is actually this itty bitty little guy in here. This is the region whose area I am trying to find. Because sure, this curve chops up the plane into a bunch of other little pieces, right? Like there's a piece between these guys here, but it doesn't have a boundary. It goes on and on forever. You could ask, well, am I talking about this region up here? Again, it's not closed in. It doesn't have a boundary. The only portion of the plane that once we draw these 3 curves is completely enclosed is the shaded one here, which is again why the graphing is important. You need to be confident what these graphs look like. If you were unsure, you could plot points, right? You could make a table. On the homework, you could use something like Desmos or a graphing calculator, but when it comes time for the test, you must know these graphs. So if I want to sort out the area of this little region, they asked me to draw in a typical approximating rectangle. That would look, I know it's small, that would look like this. Here's my little approximating rectangle. The width of this rectangle, it has a tiny, tiny little horizontal thickness. So we call that width dx. And the height of that little rectangle, we think of this as taking place at what we call an arbitrary x value. So the height of that rectangle would be the y value at the top minus the y value at the bottom. So at the top, we're along the graph 1 over x. So it would be 1 over x minus, along the bottom here, the bottom is glued to the graph 1 over x squared. So height would be 1 over x minus 1 over x squared. Now, all this means that my area is going to be the integral of, height times width, 1 over x minus 1 over x squared dx. Or you can just, again, think of it as the integral of the upper function minus the lower function. That's definitely the easiest way. That's definitely how everybody does it. The other thing I need to do is figure out my bounds. I'm integrating from where to where. So again, the idea behind the rectangle is you can imagine this rectangle kind of sweeping from left to right, filling up this area. So at the far left point in this region, x is equal to 1. And at the far right point in this region, x is equal to 2. Now you integrate from the smallest x value in that region to the largest x value in that region. So we're integrating from x equals 1 up to x equals 2, like this. Questions on the setup?
So for these problems, you're just trying to like make you're trying to make an integral based off of looking at a graph?
Yes. Yep. Yeah, so we draw the graph, shade the region whose area we're trying to find. You don't necessarily have to draw this little strip in, but I find it helps. Mostly we're doing this as training for what you'll see later in chapter 6, which is the first few weeks of Calc 2, where you're going to be doing something crazy. You're going to rotate this strip around some axis and generate a volume. Don't worry about that. We're not doing it in this class, but that's why they're asking you to do this. But yeah, you draw the graph, shade the region whose area you want, and then based on that graph, you set up an integral for that area. All right. Any questions about where any of the particular pieces in this integral are coming from? You all comfortable with where the 1, the 2, the 1 over x, the 1 over x squared, and the dx come from? Okay then. Who can help me with an antiderivative, or is there some way I should rewrite this in order to help the antiderivative? What do I do? I want to evaluate the integral. Help me out. Certainly the 1 over x is going to integrate to something related to a natural log. How about this guy? Maybe it would help if I rewrote it like this. Hang on, I'll let you know. So 1 over x, his antiderivative is the natural log of the absolute value of x. Yeah, Kevin's got the other one. This one is a power rule. Very good. Yeah, all right. So now I have a few correct answers in the chat there. That's wonderful. I'll begin by writing it like this. Definitely natural log absolute value of x for the first piece. And then I've got minus x to the, when you add 1 to this power is -2, you add 1 to that, you get -1, and we divide by that new power. So I think if we're just following the rule without trying to do too much at once, this is what we'll get. I'm sorry, my dog's about to piss himself. I gotta let him out. Now, before I go evaluating, I think it's wise to clean this up. Nobody would write x to the -1 divided by -1. This is the ln of the absolute value of x. This just makes this term negative, so it's already being subtracted, so it's going to become plus. And then x to the -1 is 1 over x. And still it needs to be evaluated from 1 to 2. Is everybody comfy up to here? Okay. Then my last moves are going to be just to evaluate. So I'll be plugging in the bounds. I'll get the natural log of the absolute value of 2. The absolute value of 2 is just 2. So that's the natural log of 2 plus 1 over 2 is 1/2. Minus the natural log of the absolute value of 1. The absolute value of 1 is just 1. So that's ln1 plus 1 over 1. This piece is 0, right? The natural log of 1 is 0. We all know that. So I have ln2 plus 1/2 and then minus 1. So that's ln2 and then plus 1/2 minus 1 is minus 1/2. And that's my answer. And this is the game. Again, really, all the money is in the picture. All right, if you can draw the picture, then you're in really good shape for these problems. So like so many things, it comes back to your skills graphing. The skills need to be there. I'd like to look at one more problem, kind of challenging area between curves problem like this, and then we're going to address the question from the start of class. What do we do if those are not both given as functions of x? Last call for questions, any part of this problem. Okay. The other one that I really like from this section in the exercises, and a variation on which you will see in the homework, is same thing, find the area of the region bounded by y equals secant squared of x, y equals 8 times the cosine of x, from x equals negative pi over 3 to x equals positive pi over 3. And certainly, again, the challenge here is in the graphing, right? Hopefully, everybody knows exactly what this looks like. It's the regular cosine wave scaled vertically by a factor of 8. But this fella, you'd be forgiven for not immediately knowing what the graph of secant squared x looks like. So I want to walk you through that somewhat gently. First, graph, good old-fashioned y equals secant of x. This is one that I formally expect you to know, but informally kind of expect you not to know. This is one of the trig functions whose graphs not everybody remembers. But given that this is an honors class, I think it is fair to say I expect you to know it. So rather than spending a lot of time showing you where this graph comes from, I'm just going to draw it. Secant x is the reciprocal of cosine x. So where cosine is 0 at negative pi over 2, positive pi over 2, 3 pi over 2, and negative 3 pi over 2. Of course, we continue like that, odd multiples of 3 pi over 2. Where cosine is 0, secant is undefined. In other words, we will have these vertical asymptotes there. Cosine of 0 is 1. So secant of 0 is 1 over 1. And cosine approaches 0 in a positive way as x approaches either negative or positive pi over 2. So secant will be going to plus infinity there. And the next kind of root point here is pi. The secant of pi is -1 because the cosine of pi is -1. And as x approaches pi over 2 from the right or 3 pi over 2 from the left, cosine goes to 0 in a negative fashion. So secant is blowing up to -infinity there. And by periodicity, we have the same thing over here. And this you kind of just stamp, repeat, and that's the whole graph of the secant function. Hopefully you guys remember this, but if not, here it is. Here's the graph of secant. How could I use this to get the graph of secant squared? Well, y equals secant squared of x is very similar to y equals secant x. You just take all the y values from this graph and you square them. In particular, that's going to take this piece and flip it up here. It's going to take this piece and flip it up here. And all of these kind of, they're not parabolas, but I know people remember them as saying like they're parabolas. All of these bowl-shaped portions of the graph of secant will be stretched out because all these y values are larger than 1. And when you square something larger than 1, it gets bigger. So the graph of secant squared, I'll draw next. I'm going to mark this as 1. And I'll put negative pi over 2 over here. It's not quite to scale, but you'll see why. Positive pi over 2 over here. And we still have our vertical asymptotes. Secant squared is undefined at the same places. Secant is undefined. And we're going to look something like this. From negative pi over 2 to pi over 2. It is an even function because cosine is an even function. And then we would continue this stuff. So if this is pi, we would have more of the same. And over here, this is negative pi, more of the same. So in black here, I have graphed for you y equals secant squared of x. I'm going to add on to this the graph of 8 cos x. Cos x, remember, is just that wave. It's the symmetric even function sinusoid. Since we have multiplied by 8, the y-intercept is 0, 8. Cosine is still equal to 0 at pi over 2 and negative pi over 2. Changing the amplitude doesn't alter that. So the cosine wave here is going to look something like this. This is the graph, y equals 8 cosine x. So clearly, the region whose area we're trying to find is the region enclosed by these curves. Which is all of this. And this problem is a great example of a problem that can be made a little bit simpler by exploiting symmetry. My art is not perfect, but you can see because these are both even functions, this piece over here is the same as this piece over here. They have the same area, they are symmetric. So rather than trying to find the whole area, I could just find this area and double it. And indeed, that's what we'll do. But before we do that, there's one other thing we need. We need to know these intersection points. So having drawn our graph, I want to find the intersection points. And we do that by setting the two curves equal to each other. So we set secant squared of x equal to 8 times the cosine of x. There is some algebra and trigonometry to do here. Secant squared is 1 over cosine squared. So this is 1 over cos squared of x equals 8 times the cos of x. And equations like these, you saw them in trigonometry not infrequently. Trig equations. Easiest way to solve this one, multiply both sides by cos squared. You get 1 equals 8 times cos cubed of x. Then divide both sides by 8. And you get 1/8 is equal to cos cubed x. And then you can take cube roots. The cube root of 1/8 is 1/2. So this is equivalent to 1/2 equals cos x. Sorry, I just let him out. So the solutions to this equation are the x values here that I'm looking for, which I'll need to use as my bounds, my limits of integration. What are the two solutions closest to 0, the two x values nearest to 0, such that cos x is equal to 1/2? Think unit circle. What's the first one that comes to mind? Where is cos x equal to 1/2? What is the inverse cosine of 1/2? Very good, pi over 3. So x is equal to pi over 3, that's one of them. And then you could, again, by symmetry, argue that the other one is negative pi over 3, or by thinking about the unit circle, or by using periodicity. There's a bunch of ways to get there. So this fellow right here is negative pi over 3. And this fellow right here is pi over 3. And they did give us those, but they didn't have to. There's no guarantee that those intersection points were the numbers they gave us. So it's really important that we do verify that. So my area here, it would be the integral from negative pi over 3 to positive pi over 3 of my upper function, which is 8 cos x, minus my lower function, which is secant squared of x, and then all of that dx. And we recognize either from the picture or from the algebra, these are even functions. This whole integrand, 8 cos x minus secant squared x, is an even function. Or again, from the picture, you can recognize the symmetry. This should be equal to 2 times the integral from 0 to pi over 3 of 8 cos x minus secant squared of x dx. These symmetry arguments are nice. They can make your life easier. I encourage you to get comfy with them, and they are fair game to ask about on exam 3. From here, I need an antiderivative. So I ask you, what is an antiderivative for 8 cos x minus secant squared x? These are being subtracted. Yeah, thank you, Tahara. These are being subtracted so we can take the antiderivative of each piece separately. If you wanted to, you could go through the process of like splitting this up, popping out the 8 from the first one. But I really think we're at a place now where we should be able to recognize fairly quickly an antiderivative for this whole thing. Antiderivative for 8 cos x is 8 sin x. Very good, thank you, Kevin. And the antiderivative for secant squared x is tangent x. So altogether here I have 8 sine of x minus tangent x. And because it's a definite integral, rather than the plus c, I put my bounds in evaluation brackets 0 to pi over 3. And you'll see here one of the ways that the symmetry makes our life easier. When you plug in 0, these are both 0. So you don't have to do as much cleaning up at the end. This, I'll write it all out, is 2 times bracket parentheses 8 sine pi over 3 minus tan pi over 3 close paren minus open paren 8 sine of 0 minus tan of 0. And as promised, this and this both contribute bupkis. Sine of 0 is 0. Tangent of 0 is 0. Here's what I want help with. What is the sine of pi over 3? Very good. The sine of pi over 3 is the square root of 3 over 2. We need to be snappy with this unit circle stuff. The tangent of pi over 3, what is that? Tangent value is a little harder. Yeah, good. Just the square root of 3. And since all of those were 0, they don't contribute jack shit. 8 times root 3 over 2. You can cancel the 8 and the 2 to make a 4. So this is 2 times bracket 4 root 3 minus root 3. 4 root 3 minus 1 root 3 is 3 root 3. So this is 2 times 3 root 3. And then 2 times 3 is 6. So that's 6 square roots of 3 altogether. So here's how that shakes out. I got you, bud. I got you. Any questions on this fella? It's a fair question, Tahara. Do we always have to graph before we get started? I would strongly recommend graphing, yes, before doing anything else, for a few reasons. One of them I'm about to show you is a little bit subtle. Sometimes it's not clear whether you're going to work with y as the variable or x as the variable. The problems we've seen so far all have our variable as x, right? These are all functions of x, but that's not always immediately clear. The other thing is that it's not always immediately clear which function is the upper, which function is the lower. So it's not obvious like which order you should subtract them. Sometimes they intersect and swap roles. Sometimes one will be the upper, one will be the lower, but then they switch, kind of like that picture we drew at the very start of class. So yes, I would say we should always graph before we do anything else. And you should draw the graphs by hand. If you're stuck having trouble coming up with the graph, using Desmos on the homework is okay. But you should still draw the graph by hand before setting up the integral. And on the test, you will need to draw the graph by hand before setting up the integral. So good question. Other questions? Okay. Then I'd like to look at some more challenging problems, specifically that issue of which variable do we play with. And to do that, I'm going to come back to an earlier example in the textbook. How's about these guys? So let's find, I'll write it down, 1/2 y squared minus 3. The area of the region bounded by y equals, what was that? 1/2. Yeah, they give it like this. Okay, x minus 1. And y squared equals 2x plus 6. This is how you might see the question phrased on a test. And there are a handful of ways to attack such a thing. Depending on how solid your pre-calculus class was, you may or may not be comfortable with conics like this. Do we have an earlier example like this? I think we probably do, maybe not. No. Definitely not. Okay. Y equals x minus 1 is definitely a line, right? You can graph this, slope 1, y-intercept -1. That's not scary. But this fella can look a little bit scary. And I'm going to try to teach this to you in the way that we talk about conics here at Santa Fe. I'm going to solve this for x. Because it has a y squared, and the x's are not squared, I expect this to be a sideways parabola, right? It is a quadratic, but it's a quadratic in terms of the variable y. So this is equivalent to saying y squared minus 6 equals 2x, which is equivalent to saying 1/2 quantity y squared minus 6 is equal to x. While I'm here, I'm going to solve the other one for x as well. Just add 1 to both sides. It says y plus 1 is equal to x. And then in order to graph both of these curves, a bunch of ways to do it. You can think about x-intercepts, that's one way. You can think about x and y-intercepts, is probably the easiest way. So we'll do it like that. But you may also remember from your pre-calculus class that this is going to be a parabola opening to the right, who's been shifted left by 6 and scaled horizontally by a factor of 1/2. All right. Again, maybe I'll use some color here. X minus 1, y equals x minus 1. It's easier to graph from kind of this understanding, but you could graph it from here as well. That's definitely a line with y-intercept -1 and a slope +1. So he's going to look about like this. So that's this guy. The other fella, again, there's multiple ways to think about it. You can ask, what are the x-intercepts? To find x-intercepts, you plug in 0 for y. So if I plug in 0 for y here, so I'm thinking about this guy. You would get 1/2 times 0 squared minus 6 equals x. 0 squared minus 6 is just -6, so this is -3 equals x. So I'll mark back here 1, 2, 3. And there's this guy. We can also calculate y-intercepts. To find these, we plug x equals 0. So here I would get 1/2 times y squared minus 6 equals 0. Multiplying both sides by 2 and adding 6, we see that means y squared is equal to 6. Taking square roots, we get y equals plus and minus the square root of 6. Now the square root of 6 is a little bit bigger than 4, so the square root of 6 is a little bit bigger than 2. So if that's 1, then the negative square root of 6 here would be -1, and this negative, we're connected this all up in a negative square root of 6. And up here, symmetric would be the positive square root of 6. So my parabola has these 3 blue points on it. Once you know 3 points on the graph of a parabola, you know the whole thing. Oh, come here. Something like this. Right, your art doesn't have to be perfect. Mine certainly is not. I'm trying to draw things to scale. This is about what we get. So here's the idea. When you look at the blue curve, it's not a function. Or more precisely, y is not a function of x for the blue curve. It fails the vertical line test. But if you rotate 90 degrees counterclockwise, this is a function. No vertical line test issues here. And this is the trick to solving these problems. That's why you see in the textbook on those exercises, it says determine whether you're going to integrate with respect to y or with respect to x. If your region is defined by curves where y is not a function of x, but x is a function of y, like in the graph here for number 4 and the graph here for number 3, then you will want to integrate with respect to y. If your curves are both functions of x, like in graphs 1 and 2, and they pass the vertical line test, then you'll want to treat it like normal, integrate with respect to x. Here, the blue curve is not a function. Y is not a function of x, but x is a function of y. So the region whose area I'm looking for is the region enclosed here. It's this space here. So this is the area I'm trying to find. And the simplest way to think about it again is to just turn your head sideways. The increasing direction of x, the positive direction for x, is off to the right. So just like when we're working with respect to the variable x, we do upper minus lower, because the positive direction for y is going up, the increasing direction of y is going up. When we're going to work with respect to the variable y, meaning we're thinking of x as the dependent variable and y as the independent variable, we want to do right minus left. Again, turning our heads like this, the orange is the upper and the blue is the lower. We turn in this direction because we want the positive x's going up. So if I turn my head this way, the orange is the upper and the blue is the lower, which means I want to integrate right minus left. So my right function is this, and my left function is this. This is the blue. So having drawn the picture, recognize that the blue curve does not give y as a function of x, but it does give x as a function of y. We realize we need to integrate with respect to the variable y. That means I need to have both of these equations solved for x, and I need to figure out which one is the right one and which one is the left one. So when working with curves where x is equal to f of y and x is equal to g of y, right, are both functions of y, we integrate right minus left rather than, God damn this pen. Upper minus lower. Because there is no clear upper and lower here. Sometimes the blue is the upper and the orange is the lower. Sometimes the blue is both the upper and the lower. But there is always a right and a left. So we're going to take this curve, thinking of it as a function of y, minus this curve, thinking of it as a function of y, and we'll integrate right minus left. The other thing we need to do is find these intersection points. So our area here will be equal to the integral of the right minus the left. My right function is this guy, y plus 1, minus my left function is this guy, 1/2 y squared minus 6. I do all of my things down. 1/2 y squared minus 6. And the integral is done dy. That's what we mean when we say with respect to y. The thing is, we need to find the y values here and here. Just like on the other problem, we need to find the intersection points to tell us our bounds. For now, I'll just call these A and B, and then we're going to solve for them. Questions so far? All right. We need to find the intersection points. And they need to be y values because I'm doing the integral dy. So I'm going to take this and set it equal to this. So I'll take 1/2 y squared minus 6 and set that equal to y plus 1. This is the same as saying 1/2 y squared minus 3 is equal to y plus 1. And that's the same as saying 1/2 y squared minus y minus 4 is equal to 0. So I subtract over the y, that's this. I subtract over the 1, -3 minus 1 is -4. To make life easier for myself, I'll multiply everything by 2. That'll get rid of this 1/2. So I get y squared minus 2y minus 2y minus 8. I'm going to have to change colors here, guys. Sorry, is equal to 0. So in order to find these intersection points, I need to now factor this. To do that, I find two numbers whose product is -8 and whose sum is -2. I think 2 and 4 will do the job with who chose the correct signs. I think -4 and +2. So y squared minus 2y minus 8 equals 0 is the same as saying y minus 4 times y plus 2 is equal to 0. So those y values are -2 and +4. Just to help see this in context, the y value right here is -2. The y value right here is +4. Which means that my integral, the integral we're looking at here, is the integral from -2 to +4, y plus 1, minus 1/2 y squared minus 6 dy. I did away with some of the parentheses there. And we want to do away with the rest of them, combine any like terms before we do any antiderivative work. That is integral -2 to 4 y plus 1 minus 1/2 y squared plus 3 dy. The 1 and 3 make a 4, and I'll write this in the sort of standard order with the quadratic term up front, so that's -1/2 y squared, then the linear term, which is plus y, and then the constant term, which is plus 4. That gets us here. And now we're ready to take an antiderivative. An antiderivative for y squared is y cubed over 3, or 1/3 y cubed. So that together with this negative half is going to give me a negative 1/6 y cubed. An antiderivative for y is 1/2 y squared. And an antiderivative for 4, careful, this is not 4x. I'm integrating with respect to y. This is 4y. And so that is what I evaluate from -2 up to +4. And from here, it's just arithmetic. We just plug this shit in, subtract what we get when we plug this shit in. So this is, I'll write it as a 4 cubed, negative 4 cubed over 6 plus 4 squared over 2 plus 4 times 4. That is what we get when we plug in the upper bound. And then we subtract from that what we get when we plug in our lower bound, which is -2 cubed over 6. So -2 cubed over 6 plus 2 squared. -2 squared over 2 plus 4 times -2. And there certainly is quite a bit of cleaning up to do here, so we should go ahead and do as much of that as we can. 4 cubed is 64, so this is -64 over 6. 4 squared is 16. 16 divided by 2 is 8. 4 times 4 is 16. There's a lot of negatives over here, so let me say minus paren, and we'll clean up the stuff inside here before we try to fix all the signs. -2 cubed is -8. So this piece would be -8 over 6. This negative will make that positive. I'm going to leave the minus out front here. So this will be 8 over 6. -2 squared is +4. So this is +4 over 2, which is 2. And then I have plus 4 times -2, that's -8. Close and close. Now I'll distribute that last negative, and I get -64/6. 8 plus 16 is 24. We have -8/6. And then here, the -8 and +2 make -6. When we distribute that, it becomes +6 like this. So altogether, I've got 24 and 6, that's 30. And I've got -64/6 and -8/6, that's -72/6. And I do believe 72 is divisible by 6, right? 72 is 6 times. No, it's maybe 72 is not divisible by 6. My arithmetic really is that bad. It's 36 times 12. That is 72, right? Yeah, 36 times 2. So that's 2 times 6 squared. So when you divide by 6, you get 2 times 6 is 12, right? Yeah. This is -12 plus 30. And when we do that, we're going to get 18. So the area between these two curves is 18 units squared. And thank you, Tahar and Kevin, for helping me with the arithmetic there. I genuinely do appreciate that. So quite a lot to this problem, right? Not a super trivial problem. The integral itself is not too bad. And that's the case with all these area problems. And the volume problems you're going to be looking at in the first week or two of Calc 2. The integrals themselves are not too bad, but the setup requires a good bit of care. So I'll come down here if anybody needs a minute or two with this, screenshot, whatever, questions. And then I want to look back at that setup a little bit more. If there's time, we'll do one more. Oh, there is not time. No, we're over time. All right. Questions on any of the work shown right now? Okay, coming back to the setup. Questions on the work here. So for these problems, sketch the curves. Decide whether you're going to do top minus bottom or right minus left. If you're going to do top minus bottom, that's it. You set up the integral of the upper minus lower. You need to make sure you know your bounds though. And sometimes that'll come from solving for intersection points. Sometimes it'll just come from the pictures. Sometimes they'll be given explicitly by the problem. If you're doing a right minus left thing, then again, you need to solve for your intersection points, make sure you understand where the bounds are coming from. But intuitively, it's not that bad. You're always either integrating the upper function minus the lower function or the right function minus the left function. Upper minus lower, your shit needs to be solved for y. That means you're thinking of x as the variable. Right minus left shit, your shit needs to be solved for x. It means you're thinking of y as the variable. I say that because you need to remember that these bounds, if you're doing a dy integral, are y values. And the bounds, if you're doing a dx integral, are x values. So when you find these intersection points, for this problem, I needed the y values there. That's the -2 and the +4. For the previous problems, to choose my bounds, I needed the x values at the intersection points. All right, that's all I have for you guys today. This is our last bit of new material before exam 3. Exam 3, remember, is going to be next Monday, 1 week from today, and it will cover everything from exam 2 to now. So that's like antiderivatives, 5.1, all the integral stuff, Riemann sums, all of it. So study guide's coming out today. If you have any questions for me, come see me in office hours. Office hour today is going to be 1 to 2 p.m. Office hour tomorrow might be a little bit weird. I don't know, because jury duty. But I'll be sure to make some announcements updating you guys with what's going to go on there. That is it. I hope you guys have a lovely rest of your day.